Some or all of you are going to last with me. How'd it go? We might get a special. Wait.
Oh no, this is not.
We may have to track down. Oh. Sorry about that. You guys have an extra day. It's okay. That's some makeup last. Oh, embarrassing. I'll make them. I'll make it. But before Doug is done, that will be fine. But in the meantime, we're going to hear about prediction.
All right.
Forecasting.
Hello again, now that you all know how to get jobs. And I'm not going to propose that space weather forecasting is really a job that you guys want, maybe supporting space weather forecasting. So let me just tell you first what is typical for a space weather forecaster at SWPC, and I'll mention a few of the other forecast centers around the globe. So in the US, as part of the National Weather Service, we operate a 24/7, 365 forecast office. So that means there's somebody sitting at the desk, looking at the data, getting the output of the models, and pushing the button to send those alerts to customers. Some things go out automatically, some are not. In general, what we would say is the forecaster is adding value to the forecast. A model run itself is not a forecast. A model run is just guidance. There are assumptions that go into that model that may or may not be valid for that particular storm. So a forecaster uses their knowledge to adjust the forecast to go with everything that they see, not just one particular model run or one particular set of data. Our forecasters tend to be meteorologists first. They typically have some sort of DoD background, and this works out well because they're meteorologists by training, working for the Department of Defense, where they get exposed to a lot of the systems that we ultimately rely on. The DoD provides some of the data, especially the radio burst data and the optical data. They run those sites, and so there's people in the DoD who have been the operators of the stations. Or they may be somebody associated with Space Command, and they're using our products to help make decisions about how to, use or not use their DoD assets. Or they're one of the forecasters that sits in the forecast office in Omaha, Nebraska, that is kind of like ours here in Boulder, a little different, but, and so there's a certain mentality to being a forecaster because our mid-shift is midnight to 10 a.m. And you'll sit that for 2 weeks. And then for 2 weeks, you'll do I don't know, maybe the swing shift, which you come in at 6 p.m., and then 2 weeks on the day shift where you come in at 6 a.m. or, that kind of thing. So it's far from glamorous. Do we have to be there? We would argue, yes, that's the current state. That's part of what I'll cover here. There are forecast offices, such as, well, many of the forecast offices around the globe only work during the day. If you're only worried about the ionosphere for businesses that are working during the day, you only need to be there when the businesses are operating. Other ones, like the Belgium Forecast Center, is there during normal business hours and receives, text alerts and things like that to tell them, when something happens, whether it's Cactus CME catalog alert or whatever, saying, hey, go look at the data. Do you see something interesting? If so, issue the appropriate forecast. The Space Radiation Analysis Group at Johnson Space Center kind of does the same thing. They get our alerts, and based on our alerts, they will then decide whether they can do something from home or whether they have to come in to support. So, but we're very much a person-in-the-loop sort of forecast office. I want to talk about the history because I think it's relevant for placing space weather in context, and I think it's just an interesting story. Go over some of the ways we forecast things today, our products, some of the challenges. I'm not sure how much of the solar cycle prediction stuff I'll cover. I chaired the last solar cycle forecast panel, and looks like we'll start up our work for the next solar cycle 25 in about the next 6 to 12 months, and then how we get our products out. So the first part of this talk is derived from a paper from George Sisko in 2007. And of course, there's a traditional way we might forecast the weather. Oh, my knee hurts, so it's going to rain. Oh, my hand is swelling. I guess there's going to be a blizzard. Oh, my head feels big. I guess there's something going to happen. But all weather starts with visual observations, then instruments. Then you bring that together. You bring multiple instruments together into a synoptic analysis. Then you add subjectivity to your forecasts, numerical weather prediction, and we're just getting to this now, and I'll show you how long it took terrestrial weather to get there. Remote sensing, in our case, was all the way back here, but for terrestrial weather was kind of the last thing to come in. So visual observations, well, here is Carrington's visual observation of the 1859 event. So, of course, he used an instrument, but the instrument didn't record it. It was him projecting, yes, actually, I've read his paper several times, projecting the image during that event and seeing the bright kernels that ended up being, the classic two-ribbon flare that caused what we now call the Carrington event. But weather guys, of course, they would go outside. They'd measure the pressure, the temperature, the wind speeds. And eventually, automated sensors took over. But even terrestrial weather was dominated by visual recordings until just about 25 years ago. So then we move on to the instruments. And here's the obvious ones that we rely on. Here's our L1 monitor, the GOES X-ray flux, geomagnetic conditions. And so this was actually a fairly famous meteorologist among meteorologists. I don't remember his name, but he's a well-known guy in the Weather Service. But then they moved on to the step of bringing the data from multiple instruments together and making maps of fronts and ridges and things like that in weather. In this case, upper air maps. Well, here's what, actually Megan is still forecasting for us, doing a daily synoptic drawing. And that's, people are like, well, why do you draw the sun? And because you can automate it. Of course you can. There's coronal hole automated algorithms. There's automated algorithms for filaments and active regions and everything. But instead, we've got the person in the loop, and they're using all the information along with what the models are telling them to come up with the best forecast. And so we believe that by drawing the sun every day and bringing together the H-alpha data, the X-ray data, the various data sets, bringing them each in onto your drawing one at a time, they're forced to look at every bit of the sun. Whereas you or I might look at the sun, see a big active region, and put all our focus there. In this case, we're really forcing the forecaster to look at everything on the sun. Is this little region over here, is it growing? Has it grown since yesterday? That kind of analysis. Still an integral part of their daily forecast. Then you get things like this. I'm not going to worry about the numbers on the weather one, but this is one of our current, it's our 3-day forecast. It's a combination of objective numbers that are in here, but it's also subjective. What are the probabilities for the KP index for each 3-hour period for each of the next 3 days? And in this case, you can see, at this period, they're calling for a G1 storm, and then 2 periods later, another G1, and then the end of the day, another G1. Late in the day, we tend to put them because there's still a bias with the detectors that bias the scale towards local midnight, which of course is driven by the fact that substorms are coming in from the tail, right? I mean, so it's biases in the data that still exist today, even though we completely understand them. But terrestrial weather, you could argue, started 200 years ago. It went through this whole process, and then late 1950s to 1960, they started to develop numerical weather models. And so they've had 50 years of developing numerical weather models to try to improve them. We put the first space weather numerical weather model into operations 5 years ago, the WSAN low model. So we are that far behind terrestrial weather when it comes to forecasting. So the idea for the models became, from on a terrestrial weather side or tropospheric weather side, this idea that obviously we can see the big stuff and we can see how that breaks down into smaller stuff, but we can only see it so far down. And yet we know there's stuff happening on the small scales that's relevant. So clearly we have to go to numerical weather prediction. And then there's remote sensing of terrestrial weather. We've all seen these images of hurricanes, and I think that's the loop that is indicative of tornado formation in radar kinds of observations. For terrestrial weather, remote sensing came very, very late in the game. And of course, we've been using remote sensing observations. It's a very, very old magnetogram, but the more modern stuff that we're all familiar with. So that's kind of the parallel between tropospheric weather and space weather and where we're at. And we're decades behind. But I would expect we're going to catch up very, very fast because they made all their mistakes along the way. And we don't have to repeat those mistakes because they made them for us. So we already know the kinds of things we need to do. So we are currently, you can break that process down into, well, you had a forecaster. That's the forecaster visual observing. Forecaster plus empirical guidance. So there might be simple empirical tools available. And I would argue last solar cycle, that's where space weather forecasting was. So cycle 23 and prior was definitely this sort of phase. forecaster plus numerical weather prediction is really where we're at right now, and we're just at the beginning of it. That will improve as you guys develop the next generation of models, the things that we currently can only just begin to do now. You guys will take to that next level, I'm sure. And then terrestrial weather reached this stage about 20 years ago, so-called head in the grids, where numerical weather prediction is giving you most of your information, and you're making small changes to that. And we're a long way from that with space weather. But terrestrial weather, that's really kind of where they are now. Where they would like to be is these last two steps where a forecaster over the loop, well, if there are things that models just can't do, the forecaster will do it, but everything else will be in the models. Will we ever get there? Well, probably eventually, in the movies, certainly. And, you know, one can imagine a future where eventually there is no forecaster in the loop. But we're not there with terrestrial weather, and we're certainly not there with space weather. So, space weather scales, you're familiar with them. Radio blackouts, radiation storms, and geomagnetic storms. So our basic forecast types of event-driven products. We have forecast products that are just like a daily forecast, like you get on the local news for terrestrial weather. But if there's an event on the sun, so the watches are most appropriate for geomagnetic storms. We see an eruption on the sun, we see a CME coming, and we see it's Earth-directed, then we can issue a watch saying, hey, conditions are favorable for a geomagnetic storm. We can't tell you that much about it. We can't tell you how strong it will be, but we can tell you approximately how strong it'll be. We can tell you approximately when it'll happen. That's kind of the level of a watch. If we had a lot of certainty, we would upgrade that to a warning. And in our case, a warning is a disturbance that is imminent. So in this analogy, it's L1, where we have only minutes, 2 hours. If the EZ doesn't go negative for 12, 24 hours, it could be that long before we really see much storming. And the conditions that we expect, we can specify with high probability. So that's watch, then warning. And then an alert is when we're actually observing. So the activity is already underway. The deflections are being seen in the magnetometers on the ground. Okay, well that's, you might argue, already too late, right? The customer needs to act, but at this point it's situational awareness. And a lot of customers like to have that. So if you go to our website and sign up for products, these are kind of the 3 general categories that you can sign up for. So the state of forecasting today is primarily probabilistic forecasting, where we're looking at the sun, and obviously, boy, this sun is looking pretty gnarly, and assess the probability of flares, and maybe there's been active CME activity, and the case of a CME, we wait for that event to occur, or even a flare, right? We can't predict flares before they erupt, and we can't predict CMEs before they erupt. At least the advantage of a CME is it takes time to get here. So you know all this, right? CME erupts. Obviously, it's on the when we think it's going to hit the Earth. We can then issue our watch product. It could be, well, we never issue them more than 3 days in advance. That's our basic product. And generally, there's not much value for most customers to know anything that much farther in advance, given the accuracy we can give them today. But certainly, more than a day prior to those conditions occurring, we will issue the watch. then, we'll see something hit our L1 monitor, and we can issue our warnings. That'll go out to the customer. And here's a nice event. I'm not sure when. I think it's just a couple weeks ago. BZ went nicely negative early in the event before turning positive. A reasonable B total. Speeds up, up to 600. So, when an event erupts, talking coronal mass ejections here, you guys learned about CCMC's tool. They do a triangulation tool. I won't get into why I think our tool is better, but I do. And it's there for you if you want to play with it. It's in SolarSoft. It's available as SWPSI Cat, SWPSI_cat. CAT stands for CME Analysis Tool. And the way this works is it brings in all available data. And in this case, Stereo B, SOHO, LASCO, and Stereo A. And you can, the shape that we use is a little different than most of the papers that fit CMEs. We use a lemniscate. It's a teardrop shape. We think it's a better shape to fit the events. And you can change the latitude, longitude, the width of the CME, and the height of the CME until you fit the data. And these marks down here show you the times of images, and you can look for the images that are taken together and use those to match an event so that you're matching images from the same time between the instruments. And from that, we determine the values we need, the time of the CME, latitude and longitude, width, and speed, to put that into the WSA Enlil model. So here's an example of a run from, this is actually even before we went operational with the model, when we were still just testing it internally. In 2011, it was a run. I couldn't tell you how well we did with it, but it had the event arriving around this time. Here's the event as seen at ACE. Here was the response of the magnetometers. Here is the actual fit to that event with the CAT tool. So that's what we do whenever there's an eruption that we think might be Earth-directed. How well have we been doing at forecasting arrival time? So in solar cycle 23, when you go to science meetings, there were various empirical techniques. The most popular one was ones were done by Nat Gopalswamy, Catholic University, who would take plane of sky speeds and basically apply something that was just a modified ballistic propagation of CMEs. There was an acceleration term in there, a few other things. But at a typical meeting, if you said, well, how well can we forecast when these things will hit the Earth? To get most people in the room to agree with you, you had to say the error bar was plus or minus 12 hours. So that was like saying to a customer, sometime tomorrow there will be a storm, but I can't tell you when. So it could be that you could go out all day and do your surveying and be fine, or you shouldn't even bother to go out because the storm will start before you even wake up in the morning. So one of the issues, and this is an important one for you guys, Nat Gopalswamy's first papers on all this work, and I'm not going to accuse him of fudging the data, but you get smaller errors in this if you use an absolute average error bar rather than what is probably a more appropriate root mean square error bar. And so when we do our analysis, we now do it both ways so that we can report both error bars. But how you describe your error bars is important, and really need it to be most relevant to the problem at hand. So what you can see is we can now forecast with the absolute average error bar a little better than 7 hours. In fact, 2015, and I'll get to that, was a bad year. It was just killing our statistics. So we were down to predicting with an absolute average error of down around 5 to 5.5 hours, right up until a year ago. So in fact, you can see that we were getting better, and the only thing I can find is that practice makes perfect, and we've just gotten better from having looked at hundreds of events. So to me, it's as much technique and expertise as just the rote mechanical fitting of events. The big thing is we removed a lot of the big outliers. So what you see is the RMS errors were quite large as plus or minus 10 hours. But now in 2014, the difference between the absolute average and the RMS errors was quite small. So we're removing more and more of the outliers. What happened in 2015 was there was no stereo. And I didn't do any of the fits, but biased. There's also very few events in the list. And so we're dominated by small event statistics, but also the fact that we were back to using just one coronagraph. So, here's what I would say to students and people that are looking for research ideas. A model like NLIL is an MHD model of the solar wind. You input the solar wind at the base of the model, and you put a CME parameterization in at the base of the model. So most people don't realize this, but the CME that's put in at the base of NLIL is a sphere. Now, raise your hand if you've ever seen a spherical CME in the data, right? So right there, it's obvious there improvements can be made. So, some of the, also, you're putting in a background solar wind. The Wang-Sheely-Argy model is a very simple empirical model. There are now many, many competitors for that, and Nick Argy is also coming out with ADAPT, a new version that does data assimilation. So we're hopeful that we'll improve things with the background wind. One of the things that becomes obvious to people is the NLIL model, you don't put in the shock, you put in the driver gas, what you might call the ejecta. And there's been a tendency in the community to fit all the excess brightness you see in a coronagraph. Well, most of that's shock, and it's not the driver gas. And so if you put that into NLIL, you're overestimating the size and density of the CME. Like I said, NLIL treats CMEs as a sphere, and both here and at CCMC, everybody uses the default densities. I won't tell you how Dujon calculates them, but they're probably not at all relevant to a CME. So there is more and more work being done in these areas. In fact, Michelle Cash has a paper she published last year on ensemble modeling with NLIL, where we varied the mass of events and showed how getting the July 2012 event to hit stereo A at the right time required modifying some of these parameters. So what I argue is if the community can find a way to produce better inputs, the model predictions will improve. And to me, there's real physics here. There's the magnetic field isn't in there. What does the magnetic field in a CME look like high in the corona? Nobody knows the answer to that question. If you answer that one, you beat everybody. So here's that July 2012 event. I think what I want to say here is this is now the modern canonical worst case storm, although it's probably not really that bad of a worst case storm. So stereo A was over here, stereo B and Earth, so nice and widely separated by about 120 degrees each. Here was the event as seen in stereo ahead. little bit up here, a lot of brightness down here. You see how asymmetric that is. Well, the standard modeling of CMEs assumes density is uniformly distributed in a CME. Well, that's clearly not right. Now, I'm not showing our Enlil modeling of this, but I'm comparing what stereo ahead observed, which is the blue, the light blue shaded region was the magnetic field observations from stereo ahead. That's B total. The red is BZ. You can see in terms of B total, oh, and then the Bastille Day event, July 14th, 2001, or 2000, sorry. Again, was one of our big events from last solar cycle. You can see B total never really got that strong. In fact, almost all of B total went into BZ. So that's why that event ended up being so strong. You can see that this July 2012 event, the BZ that hit the stereo A satellite was very, very similar to the Bastille Day event. So, and then here's the KP value. It maxed out our scale at G5 or KPs of 9. So the reason that people use this event as kind of a worst case is the B total. It's a what if all the B total went into BZ. And what if it was a different time of year where the tilt of the Earth was more favorable for a connection. So there's certainly some assumptions that go into that. So how do we forecast flares? Well, really we don't, because we would argue nobody can. We know about them as soon as they happen and no sooner. There's just nothing we can do about it. So our forecasts of solar flares are entirely probabilistic, 1, 2, and 3 day forecasts. And they're based not entirely, but substantially on classifications of sunspots. In particular, the Macintosh classification as opposed to the Zurich classification. But obviously, sunspot groups like this are much more active at producing flares than an alpha single spot that's not going to do much. So we have the statistics from these types of active regions and how many flares they'll produce at what rate, of what intensity, and that gets combined with things like recurrence and in this case, persistence. A region that was flaring yesterday is more likely to flare again today. A region that's doing nothing today is likely to also do nothing tomorrow. So you have to take that into account in your forecasting. Radiation storms, this is, I mentioned it this morning, this is the most difficult one to forecast because not all CMEs produce solar proton events. And yet sometimes CMEs headed directly away from the Earth produce protons at Earth. So knowing when a CME, we can't predict when a CME will erupt. And then seeing a CME erupt doesn't tell us whether there will be protons or not. Yes, there is a high correlation between very fast events. So there is that. But a lot of it is based on the initial observation. Most proton events do not rise so rapidly that we can't put out a warning to customers long before they cross a relevant threshold. But the current SCP forecasting are daily probabilities based on active region complexity, location of the region, and eruption history. And then we can issue warnings based on a very simple empirical model that uses the X-ray flare rather than the CME. Although, of course, there's a big correlation between long-duration X-ray flares and CMEs. So long X-ray durations, big integrated fluxes, the location and the existence of markers of CMEs, like type 2 radio bursts, will give us probabilities that an event is producing SEPs. And generally, they would like to also see some initial rise in the protons. So modeling at NOAA. WSA NLIL has been mentioned a lot. Space Weather Modeling Framework, geospace, Michelle mentioned that earlier, is running on the supercomputers, becomes operational the end of next month. And we're already seeing very good results from that. So WSA NLIL plus stereo improved the ability to forecast arrival time of CMEs by a factor of 2. So we took it from sometime tomorrow to sometime tomorrow afternoon or sometime tomorrow morning. And that's useful because, again, I'll use the surveyor as an example. If I can tell him it's tomorrow afternoon, he knows he can go out and do his surveying in the morning. So that's an economic advantage for him. So what we're getting into with the in fact, the model we're doing is the Michigan Space Weather Modeling Framework, what we call the geospace portion of that model, is enabling regional forecasts. So we no longer are limited to forecasting KP, one number for the whole planet. With this, we're getting moderately good results at being able to specify, okay, the geomagnetic storming is going to be severe over Europe at 10 UT, and it'll be 16 UT before it really hits the east coast of the United States. Exactly how that's going to work is still being worked out, but we're just getting into the realm of regional forecasting, where we're literally being able to specify by different parts of the globe how bad the activity will be. That's enabled by this kind of modeling. Whole atmosphere model is one that is being developed and is years away from being complete, where, in fact, we are taking the terrestrial weather model known as the US model, and yes, the European and UK models are far superior. The US model, known as the Global Forecast System, GFS, and extending that to 600 kilometers to include the ionosphere and parts of the magnetosphere. And so we know we have to worry about gravity waves coming up from the troposphere into the ionosphere. And so to do that, we have to couple the space weather models to the tropospheric models. So that work is being done now. And like I said, realistically, it's years away. But electric field modeling, so we don't need, this obviously a perfect sun to earth system would have all of these, but we can skip certain things. Electric field models, well, to get an electric field model for the United States, for example, we need to have the conductivity under the ground to do that well. And so there are current efforts to remap the conductivity of the Earth's crust under the United States, but there are significant gaps in that. But in fact, next year we will also have our first electric field model trying to give the power grid operators some sense of how large the currents are where their power lines are. So we're not modeling their system, we're just giving them the environmental data for their location. So this is nothing like the plot that CCMC puts up with all their models. We have a much smaller set of models. Here's portions of that atmosphere model shown here. The first bit of it will go into operations next year, probably. But a much smaller set of operational models that put us in the same part of the game for forecasting that tropospheric weather was back in the 1960s. We're going to catch up fast. So practical decisions. You're sitting on the desk, and here's what you've been observing up until this point in time. Well, clearly there was a big SEP event. Things trended down. There have been no flares of any note for the last 48 hours. Do you fly? This came down from these thresholds so you can start to fly your polar routes again, instead of diverting to a traditional fly against the jet stream and take more time and waste fuel and all those sorts of issues with an airplane. Then, of course, you guys know as well as anybody, boom, there's the flare, greater than M5, less than an X1, and there goes the protons. Except they made the call to put up that, or here, to put up that airplane and start its route over the pole. Because we made the call here, and just a couple hours later, protons went up. Well, if they haven't entered the Arctic Circle, they're now going to divert that plane to Alaska because the pilots will not be able to fly all the way from having taken off and started on the polar route. Diverting to a lower latitude route will take them beyond their legal flight times allowed. It's probably also a fuel issue. They probably don't have the fuel on board to do it. So now they've got to fly the airplane, land it in Alaska, change out the crew, refuel, remove cargo, and then continue on. Very, very significant efforts. So they would like to have known about that solar energetic particle event back here, 12 hours before it occurred. Well, can do that. Great. Love to have it. So I already talked about this. Our forecasters, I try to let our forecasters do as much of this as possible. I worked on SOHO since before launch on the LASCO coronagraphs. I've seen more CMEs than probably everybody in this room combined. And to me, that makes it a heck of a lot easier for me to do these analyses with the CAT tool and get the inputs we need. But we need to train other people. So I try to let the forecasters do as much as possible. And so sometimes they do better than other times. So we have all sorts of training issues, experience. Big issues are LASCO is not operational, neither is stereo. So we can sometimes wait a long time for events. And there's nothing like playing in a softball game on a Tuesday night at 7 o'clock and getting a call that we just had a type 2 burst reported at 3,000 kilometers per second. It's like, okay, well, you re-recognize type 2 radio speeds are highly unreliable. And then it's like, okay, what do we see in LASCO? Oh, well, we're not going to have any data for 6 hours. Okay, well, if the CME is really traveling that fast, then it's probably going to get here in about 17 hours. And we've just given up a third of our time for doing the analysis. For that particular event that I'm referring to, I used the type 2 speed of 3,000, used the source location of the flare, used an average CME width. Actually, I used our maximum CME width that we've observed, and did a model run. We did not push it out to the public. That would have been scaremongering and potentially dangerous, causing all sorts of people to take action before we had full information. Kept it internal. And then as soon as the LASCO data came in, the CME had been traveling that fast. In 6 hours, it would have already left the field of view. So when I got the very first image, We saw the CME was still in the middle of the field of view. We knew the speed was not 3,000 kilometers per second. And we knew we had time to redo the analysis and redo a run and put out a more appropriate forecast. One of the things we have to be very careful of is FEMA, the White House, power grid, they're all going to react. And so you've got to have confidence in your forecast, but also a willingness to issue and push that button for a G4 or a G5, because failure to do that is just as bad as doing it inappropriately. So, geomagnetic storm intensity forecasting before we see it. Yep. Well, I think it's fair to say we have never missed a big event yet. March of '89, we forecasted. I think even August '72, I think, was forecasted. What's different today that didn't really exist back then is between 1972 and March of '89, everybody in the power grid kind of forgot about space weather and wasn't as aware. And then from '89 to 2003, I would say awareness stayed around. And so when we issued our warnings and our watches, they were alert and prepared. Yeah, I think it's fair to say we have never missed a big event where we've had egg on our faces. There have been instances where other agencies sounded higher alarms than we did, and then we had everything. We had the White House like, "Hey guys, what's going on? Tell us, is this that bad or not?" And thankfully, we ended up being right, and now listen to us a little bit more. But so we're trying to use WSA NLIL. A direct hit versus a glancing blow is going to be a stronger event, but lacking the magnetic field observations. So we really need, that's where we're data starved especially. It's really, really hard to do that. So trivial things like the speed of the CME, which isn't really highly correlated with the mag field, are all we really have. We have to worry about what would we do, how would we model CMEs if we lost SOHO. So that's why one of my main things is to get a coronagraph up before we lose SOHO. We use stereo, we use anything we can that would fill in the gap, even those type 2 radio bursts, as unreliable as they are. So here's an example of what we typically do. So here's an NLIL run from January 2014. Almost certainly the forecaster did the first run of NLIL. Might have been me, using the first 3 images available. And it predicted arrival time at 5 UT on January 9th. So the event was on the 7th. Sorry. We expected arrival on the 9th. We did another run later when we had more data, predicting the arrival about 7 hours later. Overall, that's not really that much. And then, again, whether it was a different person or whether we had more data, we did another run of the CME. So we tend to call these mini ensembles. And it ended up splitting the first 2 and ended up being, really, I would argue we ended up with tight grouping on this. The differences between all these runs ended up being very similar. That's the event as seen in LASCO. You see West Limb event, not a strong Earth-directed component. And other than the fact that it was a gap in magnetometer data, which is very, very unusual, absolutely nothing happened. That was what you call a total bust. Here's an event. I guess this is an example of a total failure in the opposite direction, where the forecast that was put out on February 18th at 22 UT, so right there, said geophysical activity forecast, the geomagnetic field is expected to be at quiet levels on days 1 and 2, and quiet to active levels on day 3, and then boom. So G2 can almost get away with that. We don't. In fact, anything G1 or higher that we miss counts against us in our reporting to Congress. So it's a big deal for us. All right, so that's kind of my overview of how we try to predict today and especially predict geomagnetic storms. I'm going to quickly go through solar cycle forecasting. I think it's kind of fun. Something we only do about once every 10 years. Yet so you would think every 10 years, boy, a lot of progress has been made. So now we can do stuff better. And that's definitely not true. So I think I'm going to even cover this. There are still people that try to tell me that the positions of the planets has something to do with solar activity. Okay. Yeah, that's about all I can say about it. Statistical treatments of past solar cycles, what I would call numerology. Not totally invalid, but one has to be careful. Phenomena during the previous cycle, what we call precursor techniques, well, that's starting to use some science. And these tend to be the things that work best, actually. Or phenomena around sunspot minimum, another totally new different set of precursors. If we wait for the cycle to begin and we get a couple years of data, you can be very accurate about how intense the cycle will be. And then the last solar cycle, when we tried to predict cycle 24, these new models known as solar dynamos, in particular mean field models, became available. Oh, so if we go back, these were all the predictions that were made for solar cycle 21, and you can see everybody predicted from a low of about sunspot number of 30 to a maximum of 200, and an average solar cycle was right in here. So somebody was going to be right. Statistical predictions accounted for 11 of the 38 predictions in cycle 21. We're looking at time series of past activity, and the assumption is the sun will continue to behave as it always behaves. And the simplest statistical method would be to average all cycles together, or people would pick all odd cycles, or pick the n most recent cycles. You can be a little more sophisticated and apply, spectral methods to that, like Fourier analyses or other things to that. Be more rigorous in your analysis. And so here's an example of spectral analysis done in the 1970s of the sunspot cycle to try to make predictions. And then people use what's known as the Gleisberg cycle, have used in the past, this to try to forecast and show that there's this sort of 100-year period in solar activity, which has at least partly gone away now that they've reanalyzed all the sunspot numbers and tested them. So that this idea of a modern maximum has also gone away. So the solar cycle 24 prediction, actually I'm not sure why this is coming up next. was for a below average solar cycle, which it turned out it certainly was. So we'll get there. Oh man, you can't read that. So what this was supposed to be showing is meridional flow takes magnetic field from the active latitudes and transports it towards the poles. That gives us our solar cycle. But that's what also has become clear, has become what's also the seed particles for the next solar cycle. Here's a better way to represent that. And so you can see that the polarity at the North Pole was negative polarity, at this phase of the cycle, and then the positive fields from the next cycle came up and dominated, replacing the negative fields with positive, and then next cycle the negative fields came up and dominated. So classic 22-year solar cycle pattern. Of course, we're more interested from activity in the 11 years. The figure showing meridional flow, function of latitude, in meters per second. So it's a very slow flow, but it has years to act. So precursor techniques were used about a third of the time in cycle 21. And in this case, they typically used recurrent activity. And today we know that to be the activity coming from coronal holes that persist. So one might ask themselves, what is it about coronal holes that allows us to forecast solar cycle activity? Well, somehow that's rooted in the magnetic fields. And so there are various techniques for looking at that. And again, it was assumed to be somehow founded in the mag fields of dynamo theory, where the poloidal field of cycle n is converted into the toroidal field of cycle n+1. But I would argue there's still no direct physical causal shown. A lot of hand waving. But, go back decades and see that people were doing this where they correlate, in this case, the Wolf number is the sunspot number, and this is a measure of geomagnetic activity. I don't remember exactly which index was used here. But you can see there is a nice linear correlation between sunspot number and different measures of activity. So clearly, we should be able to predict with that. Again, somebody else doing it a different way. If we look at initial progress of the new cycle, well, that's just cheating. Well, not really, but people want, if you're designing a satellite for the next solar cycle, you want years of notice when you start your design. And you want that lead time. So one of the most common ways of doing that is known as McNish-Lincoln, which up until last year was published monthly by the National Geophysical Data Center. That old Fortran code has broken. They came to my office a couple of weeks ago and want my help getting that back together. We'll see if I have the time. But the reason that works, and this is work done by David Hathaway, showing that there's a nice functional form to describe the solar cycle. And so a cycle of amplitude A has start time t0 with a width b and an asymmetry c provides a prediction for the current cycle and can account for systematic changes in the cycle shape. And it turns out the asymmetry is a constant of 0.71, and the width varies with amplitude. So there's really only two parameters left you have to worry about once the cycle has begun, the amplitude and the start time. And so what this plot shows is, I lost my laser pointer, about 30 months after the start of a cycle, that becomes a very good predictor of the way the rest of the cycle is going to behave. So not initially, but it gets better and better as you go along. So that's certainly one way you can forecast the cycle. Precursors, one of the more modern techniques is to use the polar field strength directly. So instead of using the equatorial coronal holes that are giving you your recurrent geomagnetic storms at Earth, why not go straight to the source and measure the polar fields? And so now this is not a recent plot. You can see how the fields vary, and before the last cycle, the polar fields were weak, and lo and behold, cycle 24 was weak. And so this looks to be a very promising precursor technique for forecasting. Let's skip neural networks. Back in 2004, somebody in this building, actually, Nausumi Dikpati, published a prediction for cycle 24 using her flux transport model. And this is a figure from her paper showing the meridional flow and the idea that the speed of that varies under the surface. And so I'm actually very attracted to this because this is a way you could combine the positive and negative fields, have them start to run into each other and cancel, and generate, a weaker total field that can then be a seed for the next one. Thing is, her model was predicting that the next cycle would be larger than cycle 23. And of course, that was exactly the opposite of what really happened. But these mean field models of dynamos are difficult, and there's a lot of papers now, and you can almost come up with any answer that you want to. So the key to forecasting is to come up with an answer, make a prediction before a solar cycle begins. But here's what we were dealing with, much like several decades ago. Predictions all the way from about a sunspot number of 40 to about 185. It's covering pretty much the full spread. A whole bunch of them right around the average cycle, and all these different ways of predicting the solar cycle. This is what we issued in 2009 for the forecast of the cycle, a peak of around 90. So we had forecast a peak of 90 in May of 2013. The actual peak was 82 in April of 2014. So we did put an error bar on our prediction of plus or minus 10. So in fact, we were inside of our error bar. So I call that a win. I would argue we got lucky. Big thing about this cycle was the timing. And we were out by a full year. And we had thought we could forecast to within plus or minus 6 months. Now, the solid line is the smoothed monthly number. The points, the asterisks, are the monthly sunspot numbers. Then the red is the prediction. Actually, early on in the cycle, the prediction looked good. The initial part of the decline, it looked good. But right here, it got it completely wrong. And the reason, I think I put it in here, is we assumed there was one sun. Of course, there is only one sun. But when you're trying to predict things like this, you have to recognize the northern and southern hemispheres can be very, very different. So if you want to, and in this case, that second hump, and so northern hemisphere, so the total sunspot number is the black line. Sunspot number in the northern hemisphere in the last cycle is in blue, and you can see that peaked back in 2011, September of 2011, at a whopping sunspot number of 41. Southern hemisphere didn't peak until 3 years later. So, and it ended up being larger, 57. It turns out if these had peaked at the same time, our forecast would have been almost dead on perfect. But one of the things we didn't consider, we acknowledged it when we did our forecast for this cycle. But there are very few papers in the literature that are addressing it. And we can only use what people are putting in to the literature. So that's a good message, I think, for you guys. Get it out there so that people can use it. So you have to consider the hemispheres. Will we be able to use it for the next cycle? Maybe, but maybe not. The issue of which cycle is leading is the south led for these periods, then the north, then the south, then the north, and periods we don't have good data for. So, but they're out of phase pretty often. So certainly something that has to be considered. Okay, so where are we today? Here are the polar fields at the last solar minimum. And here are the polar fields as of about a month ago. So we've already reached a polar field strength equal to last cycle. So the next solar cycle is going to be at least as strong as cycle 24. That's my personal opinion, not an official forecast. But to me, it looks promising. You can see the current cycle is actually dropping off more rapidly than we expected. But there's really no evidence that cycle 25 is going to start anytime soon. We think we're a couple years away. Last thing, disseminating our information, even the solar cycle forecast. So it's on this website, right? So yes, we'll pick up the phone and call the most important customers, which this is actually backwards. The most important customers would be the folks that run the power grid and FEMA. And then these other guys get called after that. You guys, as well as everybody else in the world, can sign up for our email alert system. So our product subscription service is a no-cost service. It's email-based, although we may switch that to something, a more modern technology sometime soon. Of course, the website is what a lot of people use to see what's going on. Of course, we've entered the age of Facebook and Twitter, but those are not our official product dissemination means. Our official products are represented by these first 3 bullets. And of course, we do active media support during significant events. So yeah, very few phone calls. The product subscription service emails. So here's our product subscription service. You can sign up for advisories, Space Weather Outlook issued once a week, Space Weather Bulletins not issued very often, forecasts, plain language forecasts, as well as coded message forecast products that go out, the weekly highlights, of course the radio blackout, geomagnetic storm, and solar radiation scale products, the watches, warnings, and alerts, summaries, event, after the fact sort of recap, electron alerts, solar radio alerts, and general news. Go to our website and you can sign up for any of these. So, summarize, solar flare radio blackouts. No advance warning, probabilities only. Impacts, very limited in time and on the daylit side of the Earth. Radiation storm scale, the S scale, warnings of minutes to hours are possible, can last for days. Geomagnetic storm scale, Well, we assume the worst case will be just under a day. That extreme event that'll take 17 hours to get here. But a typical event is going to take 3 or 4 days. Talked about the impact. So this is where it's done. South Boulder, that's our forecast center. We have more monitors now than we did a couple years ago. And the view from our building of the mountains. So just to make you all jealous, if you like snow. Thanks. Did intentionally limit this to close to an hour, just so you guys could finish early. Any questions? What's my favorite thing? The thing that motivates me is that, you know, what I always have to remind myself that, well, there's two things. There's the overall motivator. People are like, you're in the Department of Commerce. Why are you there? Why are you not in NASA? Isn't it research? Yeah, but it's about the industries being impacted. And it's about making a difference, saving some money or keeping the lights on. I mean, being able to know that every day when you wake up, you might make that sort of difference. Sort of thing that motivates me. I love going to work. Now, a CME erupts. I'm one of those people the forecasters will call at 3 in the morning and come in and do an NLO run or help them out with the media. And I get very into that whole, let's get this fit done, get the CME run on the web, get the forecast out, get the watches and the warnings out, and then I've been known to do dances when the event arrives and the NLO run matched perfectly. We do a 9:10 briefing every morning. Forecasters give it, and the NLO runs anytime we dance in front of the whole lab. Anybody else? Yeah, I mean, I think there's a lot that can be done for forecasting. You know, one hope, the Space Weather Action Plan got mentioned this morning. Reality is a lot of the research funding is for research. And so if you put very little of a forecast element you can put into it, there is a workshop in 2 weeks here in Boulder. We're hosting it, driven by the Space Weather Action Plan. We're calling it the O2R workshop, Operations to Research. What we're hoping, now I say this because we've been hoping for about 5 to 7 years now, is that we're going to get money so that we can start paying researchers to solve some of these practical problems for us. It may not be a pure research topic, but more of a practical, applied research activity, where we're giving out grants for 1 to 2 years to come up with a better model for input into NLO or validate some prediction tool that's out there. Workshop, which is going to be here in Boulder in 2 weeks, is designed to get community input on what that O2R facility or center needs to look like. And so ideally, that's going to be one more source of funds for researchers in the future. Hopefully we can pull it off. Yes. So all the models are different, and I can't really speak to the atmosphere models. But with NLIL or with geospace, well, let's start with NLIL. NLIL is driven entirely by the inputs. You do have to, the current version, although there is now a newer version that you don't have to spin up from steady state, wastes about, well, half of its runtime is spinning up from the initial conditions to the current condition. But it's really driven entirely by the inputs of your magnetograms into WSA and the model of the CME. And you don't really have to, well, you do have to worry about some history. Prior CMEs can have an influence. In fact, that's a limitation. This ensemble modeling that I mentioned that Michelle Cash had done for the July 2012 event, the NLIL model gets that wrong because there was a CME 3 days before the July 2012 event that disrupted the streamer belt. But because NLIL basically puts in a sphere, as soon as the back end of that sphere has crossed the inner boundary, the NLIL model reverts to background solar wind conditions and reforms the streamer belt. So the July 2012 event always runs into the streamer belt in the model. But when you look at the data, there's no evidence of the streamer belt in front of the CME. It's been completely disrupted by the previous event. And so there are elements of the model that are clearly wrong that would have prevented getting a good forecast. Geospace modeling, definitely have to have more of a history to the magnetosphere. It's relevant, the preconditioning of the magnetosphere. Not really sure of the timescales involved. One of the things about running those models in real time is you're getting, say you're getting solar wind at 400 kilometers per second at L1. You run your model, that's going to tell you what things are going to be like an hour from now. And then a shock, at call it 800 kilometers per second, it's this satellite. Well, that's going to arrive in 30 minutes. So you actually have to reset the model, go back in time, and rerun it with the right conditions. Because now you've got solar wind that's more extreme that's going to get there before the previous run of the model even valid for. And so there are lots of practical operational issues that we find researchers never encounter because they never actually try to do these. Yeah, and that's, probably the biggest point to make is, because I used to do this. When I worked at NASA as a contractor, of course, my two favorite websites, I like to say in the morning, dating myself, were Astronomy Picture of the Day and Today's Space Weather. Today's Space Weather doesn't exist anymore. I think APOD still exists, right? So, and something would happen, and I was a researcher. If I wanted to spend all day looking at one event, I could. Our forecasters don't have that luxury, right? They've got to do their analysis, make their decision, and move on and deal with the next thing. And so it is about getting the information in front of the forecaster, coming up with the best decision at the time. It's very easy to second guess after the fact. People do it all the time. That's one of the things I'll say. Forecasters have very thick skin. They learn how to take that criticism because they've all screwed up forecasts, whether they were doing tropospheric weather or space weather. I've kind of learned that as well. So we're going to make mistakes, but things are definitely getting better. Numerical weather prediction, the modeling. There was a conference here in Boulder about a month ago, maybe 2 months ago, the Quo Vadis meeting. where are we going in Latin. And it was the National Science Foundation attempt to figure out what the next big facility needs to be. And I got up and said, hey, wait a second, you can build all the facilities you want, but we'll always be data starved. As long as we're trying to live with data, we'll always be limited. And if we try to do it all with models, we'll be limited. It's when we bring them together. So data assimilation, bringing the data and the models together, I think, is really where we have to be. Tropospheric weather has been there for a long time. We're just beginning to do baby steps of that in space weather. Ripe research areas there for people as well.